Welcome to the Explainer. Today, we're jumping into the story behind Cursor Composer, a new AI coding agent. We're going to look at how its creators tackled a really fundamental problem with AI coding tools to build something that's both ridiculously fast and incredibly smart.
Okay, so let's kick things off with a feeling I'm sure a lot of you developers out there know way too well. Using a lot of the early AI coding agents feels just like being stuck on a plane with terrible Wi-Fi. Yeah, it technically works, but it's so slow and clunky that it just pulls you right out of your focus. It's so frustrating you almost wish you didn't have it at all. In this whole airplane Wi-Fi experience, it's not just a funny analogy. It really gets to the heart of the core dilemma that's been holding back AI coding tools for a while now. For a while, developers have been caught between a rock and a hard place. On one side, you had what you could call the cheetah slug, agents that were super fast, but honestly just not smart enough for real work, constantly interrupting you with useless suggestions. And on the other side, you had the legacy agent. This thing was incredibly smart, but painfully slow. We're talking 10 to 20-minute waits that would just completely destroy your concentration. Neither one could keep you in that creative flow state. So the team at Cursor looked at this frustrating choice and basically said, nope, this isn't good enough. They decided to build a whole new kind of agent, one that could finally solve this trade-off. And their answer is Composer. It's an AI model built from the ground up specifically for how software engineering gets done day to day. The whole goal was to finally deliver both speed and intelligence, so developers can actually stay in the zone and get work done.
So how on earth did they pull it off? Well, the secret sauce here is something they call parallel tool calling. Instead of doing things one by one, read a file, then read another file, then search for something, Composer can do a bunch of stuff all at once. It can read 10 files, search the entire code base, and check for errors all at the same time. It sounds simple, but this one idea makes the whole experience feel so much faster and more alive. But okay, having a bunch of cool tools is one thing. Actually teaching a model how to use them and when to run them all at once, that is a seriously complex challenge. And to crack that nut, they turned to a really powerful technique from machine learning called reinforcement learning, or RL for short. And the basic idea behind this is surprisingly simple. You can almost picture it like a training montage in a movie. The AI gets a task, it tries out a series of actions, what's called a rollout, and then its final work gets a grade. Based on that score, the model gets a little tweak, learning to do more of what worked and less of what didn't. It just repeats this cycle over and over, getting a tiny bit smarter each time.
Conceptually, it makes perfect sense. But here's the catch. The real engineering beast wasn't the idea itself. It was figuring out how to make this whole process work at a massive scale. We're talking huge models, thousands of powerful GPUs, and real, messy, complicated software projects. And this right here is where the story gets really, really interesting. Because the biggest roadblocks they hit, the hardest problems they had to solve, they weren't actually machine learning problems. They were infrastructure problems.
So let's break down exactly what they were up against. First, just raw speed. Training a model this big is brutally, painfully slow. Second, complexity. Real-world coding isn't clean. A single request might involve millions of tokens and hundreds of different tool calls, all finishing at different times. And third, and this one is absolutely crucial, consistency. For the model to learn properly, its training playground had to be a perfect mirror of the real product.
And this is the core insight of their entire project, the big reveal. For every single one of these classic machine learning problems, the most powerful and effective solution they found was an innovation in their infrastructure. So what did this infrastructure actually look like? Well, they designed this really clever 3-server system. You've got the trainer, which is like the coach, updating the model's brain based on how well it did. Then there's the rollout server, which is like an air traffic controller, managing all the different attempts the agent makes. And finally, you have the environment servers, a whole fleet of virtual machines that act as the perfect simulated practice field. So to solve that first massive problem, speed, the team actually got their hands dirty and developed custom software, these things called kernels, to make the training more efficient. And the result was a mind-blowing 3.5 times speed up on new hardware. That's what made this whole thing possible in the first place. All right, next up, complexity. To handle all those messy, unpredictable tasks, they built a smart load balancing system. Basically, it makes sure that if one task is taking forever, other GPUs aren't just sitting around twiddling their thumbs. It keeps shuffling the work around to make sure the whole system is running at max capacity all the time.
And for that final critical piece of the puzzle, consistency, they had a stroke of pure genius. They just repurposed their own commercial product, their cloud agent system. These secure, sandboxed virtual machines became the training environment. It was the perfect replica of the real world, because it was the real world.
So, after all of this incredible, behind-the-scenes infrastructure work, what was the actual payoff? Did it really lead to a better experience for developers?
Oh, you bet it did. This chart really shows the model's incredible journey. It started out performing on par with the best open-source models out there. But because they had this amazing infrastructure for continuous learning, they were able to just keep iterating, pushing its capabilities way up, getting it incredibly close to the best, most powerful models available today.
But what's really cool is that the improvements weren't just about higher scores on a chart. The model literally learned to have better behavior. It learned on its own to use tools in parallel, making it feel faster. It learned to be smarter, to actually read and search through more files before it started editing code. And because it was trained in its native habitat, it became a true power user of its own specialized tools, like semantic search, in a way a generic model never could.
And this whole massive effort was guided by a refreshingly clear and focused philosophy. The point here was never to build AGI, or artificial general intelligence. It was to build a tool that is exceptionally, almost obsessively good at one specific, complex job, helping humans write and edit code.
When the Cursor team looked back on this whole process, they walked away with 3 really powerful insights. First, for specific jobs like coding, reinforcement learning really works. Second, using your own AI tools to build AI tools creates this amazing flywheel effect that just speeds everything up. And third, and this is the big one, so many of what we think of as machine learning problems are, at their very core, actually infrastructure problems in disguise.
And that really leaves us with one final massive question to chew on. If building the next generation of incredible AI isn't just about who has the cleverest algorithm, but who can build the best, fastest, and most realistic underlying infrastructure, who is actually set up to win that race?